look for the final version. Okay, so this is lectures about cosmological gravitational particle production. And let me unpack that title a little bit. So cosmological meaning it will be particle production during the Big Bang in the early stages of the universe. Gravitational implies that particles will be produced only by gravity. The only force that will be acting to produce particles in cosmology in these models will be gravity. And particle production sort of explains itself. So the idea is to have models for the early universe where only gravity produces particles. So what is some of the motivation for this? Well, as long as I can remember, I've been working at something that we like to call the inner space, outer space interface. And the inner space involves particle physics, and the outer space involves the universe and cosmology. So what is the interaction between the inner space and outer space? So it's clear what this means. I don't have any idea what this is supposed to illustrate, but it's a cool looking photo. So the idea is that particle physics, inner space, is necessary to explain the universe. So we won't understand outer space without understanding inner space. And I'll just list 5 aspects of the universe today where particle physics plays a role. One is the existence of dark matter. The other is understanding dark energy. A third is trying to explain the baryon asymmetry, why our universe today is asymmetric in the number density of baryons and antibaryons. Particle physics and inflation is necessary to understand the properties and existence of fluctuations in the cosmic microwave background radiation, and also the origin of structure in the universe. Why are there superclusters of galaxies, clusters of galaxies, stars, planets, people, etc.? And well, the answer to that question is it all comes from quantum fluctuations in the early universe. So why are you here? You are here because you are an amplified quantum fluctuation. Pretty cool, right? You're a quantum fluctuation. You're an amplified quantum fluctuation. So this is how particle physics is used in cosmology to understand the universe. So this is going in this direction. And also we can use the universe as a particle physics laboratory. So it's often said that the Big Bang can be used as a particle accelerator to produce particles which perhaps, because of small interaction cross-sections or large mass, cannot or have not yet been produced at terrestrial accelerators. The universe also provides a laboratory to study particles with a very long lifetime or particles that have a very long interaction path length, very weakly interacting particles. It's also used as a laboratory to study limits on models for beyond the standard model. And we can use stellar stars and objects like that, stellar energy loss in particular, to limit the properties of weakly interacting low mass particles. The universe also has, in the existence in the universe, there are regions of the universe which have very, very large magnetic fields. So we can use those, larger than can be produced in laboratories, to study the interactions of particles in large magnetic fields. Okay, so a brief history of the universe on one slide. And I think of this as a cosmic symphony with several movements. So the earliest movement that people talk about, the tempo may be plucked strings, sort of string-dominated cosmology. And what is the age of the universe at this time? Presumably it's comparable or smaller than the Planck time. Then there was believed to be a movement of the universe that's dominated by vacuum energy, known as, and this is inflation. And this is a very rapid movement for the expansion rate. We don't know when this occurred or why it occurred or how it started, but typical times and ages is believed to be about 10 to the minus 35 seconds after the bang. And the temperature is hard to understand what a temperature was in the string-dominated phase, but the effective temperature of the universe during inflation is h over 2 pi, where h is the expansion rate. So what are the relics that would have been produced during the string-dominated phase? Well, one thing we'd like to understand is why are there 3 large spatial dimensions? String theory seems to be formulated in 11, 10, 11, 26, some large number of dimensions. What happened to all the other spatial dimensions? How did we end up with 3 large spatial dimensions? The relics for the inflationary era include CMB fluctuations, cosmic microwave background fluctuations, possibly primordial black holes, primordial gravitational waves, and the seeds of structure, the quantum fluctuations that lead to structure, and perhaps dark matter. We don't know where dark matter arose. The vacuum, we know a lot about inflation, except we don't know when or how it started, and we don't know when or how it ended. But when it was happening, we know a little bit about by cosmic microwave background fluctuations. And, but the vacuum inflationary phase ended presumably with a short matter-dominated phase with a less rapid expansion rate, something like larger than 10 to the minus 35 seconds. We don't know what the maximum temperature to define here, and what was produced here, possibly dark matter and possibly the baryon asymmetry. Sometime after the matter-dominated phase was a radiation-dominated phase that lasted until sometime smaller than about 10 to the 10,000 years after the bang. And the temperature, the maximum temperature during this phase is known as the reheat temperature after inflation. And what was produced during this phase, possibly dark matter, light element abundances in Big Bang nucleosynthesis, and perhaps a baryon asymmetry. Then the universe became matter-dominated with a slower expansion rate and was matter-dominated after about 10,000 years after the bang, when the maximum temperature was about 9,000 K. And the relic from this that we can study is the growth of structure. Finally, the phase that we're in now is a walking phase, a slowly expanding phase, again, dominated by vacuum energy, not inflation, but dark energy would probably be a better description. And on cosmological scales, it started more or less the day before yesterday, a billion years ago or so. On cosmological time scales, 1 day, a billion years, it's all the same. And the maximum temperature here was about 4 degrees Kelvin, and the relic, the observational relic, has to do with the expansion of the universe. So on one slide, this is a history of the universe, but I'm not going to cover everything, of course. During these lectures, I will concentrate on inflation and the matter-dominated phase. So these are the eras in the history of the universe that will be important for these lectures. So let me give you a short list of ways that gravity can produce particles. So one idea for gravitational particle production is known as a misalignment mechanism, where production of a scalar field, let's say, is due to the fact that during inflation, there are quantum fluctuations in the scalar field. I'll derive this in a little bit of detail, but during the early universe, the equation of motion of a scalar field is phi double dot plus 3h phi dot plus m squared phi is equal to 0. So this is just a free scalar field with mass m. So it's not quite, because of this term here, 3h phi dot, h is the expansion rate, because of that term, it's not what you would get in Minkowski space. During inflation, the scalar field has quantum fluctuations, and the typical fluctuation in the scalar field is h over 2 pi. So during inflation, we do not expect the scalar field to be at the minimum, but we expect it to have regions of the universe that are displaced from the minimum, possibly at some initial value phi sub I. So after inflation, the field will have a value here, but if you look at the equation of motion, the field will be frozen at this value because of something that's known as Hubble drag, the 3h phi dot term, and it won't start oscillating around the minimum of the potential as you would expect until h is approximately equal to m phi. So as h decreases, eventually this term will dominate and it will oscillate, and it will have energy density in the oscillating field. And an example of this is a production mechanism for axions that presumably we will hear about. Oh, wrong way. Here's another idea for gravitational particle production that I will cover in a little bit of detail later. Black holes produce particles due to black hole evaporation by Hawking radiation. Now, if primordial black holes are produced in inflation, then eventually the primordial black holes will evaporate, and it will evaporate and produce all sorts of particles, whether those particles have interactions with the standard model or not. Again, this is only gravitational. And there was a recent series of papers by some of my colleagues from Fermilab, Dan and Gordon and Sam, and they calculated omega h squared, say that there's some particle that only interacts gravitationally and is stable. What would its value of the present density be, omega h squared? And if it's dark matter, 0.12 is the value that you would expect. And in some model calculations, they have it depends upon the mass of the particle, the initial temperature when the black hole starts to emit the particle, and the efficiency of forming the black holes during inflation. And they take 10 to the minus 16 as a reasonable efficiency, T sub I and M, model dependent, but this would be sort of the figure of merit for omega h squared over 0.12. So what is the dark matter? If the dark matter is a particle that only interacts gravitationally, then this would be a mechanism to produce it. Now, has been a lot of recent interest in primordial black holes, particularly after the first LIGO detection of gravitational radiation from the in-spiral of black holes. And these were 30 solar masses black holes, which were thought to be difficult to produce in the post-Big Bang universe. But now it's not so much of an issue, but it generated a large amount of interest. And the seeds for primordial black holes would come from inflation, but this would be a nice mechanism. You know, if the dark matter mass is very large, about 10 to the 11 GeV, and particles with mass of 10 to 10, 10 to the 11, or 10 to the 12 GeV are more massive than WIMPs that are usually considered to have electroweak scale masses. So they're known as WIMPzillas, really big WIMPs, WIMPzillas. They'll step on you if you're not careful. So this is an idea for gravitational particle production. Another idea for gravitational particle production is that you can produce dark matter from the standard model plasma just due to graviton exchange. So the idea particles have gravitational interactions, and the standard model particles from the standard model plasma would have an interaction strength of proportional to 1 over the Planck mass. I'll go into detail of this later. And the dark matter also has gravitational interactions. So you can imagine just from the primordial plasma of standard model particles that the standard model particles can produce dark matter just through graviton exchange. And Garni et al. Calculated this. The reference is in the review article. And it's a freeze-in calculation. And it's for dark matter masses around 10 to the 13 GeV. And it depends upon the reheat temperature, but you have to assume that the reheat temperature is smaller than the mass of the particle in order for this to be kinematically allowed. So after inflation, the universe reheats, and the maximum temperature of the radiation-dominated universe is known as the reheat temperature. And we don't know what that is, but in this model, you have to assume that the mass is smaller than the reheat temperature. Another mechanism to produce dark matter through only gravitational interactions is, rather than starting with standard model particles in the initial state, after inflation ends, the universe is dominated by the energy density in the inflaton field, in the scalar inflaton field. And the energy density in the scalar inflaton field is a cold inflaton condensate. And from the cold inflaton condensate, through the same type of interactions, you can produce dark matter particles. Again, this only works for dark matter masses smaller than the inflaton mass, and the dark matter mass for the correct value to be the dark matter of omega h squared involves a function of several parameters. There are two approaches for calculating this. One is the Boltzmann approach that Emma Nakayama and Tang and Mambrini and Olive did. But this is not the complete treatment. This is just a subset of what I will talk about in gravitational particle production, combining the work of Schrödinger and using Bogolubov transformations. So now let me talk about the main topic of these lectures, and this is gravitational particle production through something an idea that was pioneered as long ago as 1939 by Schrödinger. In 1939, Schrödinger wrote a paper called The Proper Vibrations of the Expanding Universe. And this was the first paper I'm aware of that pointed out that the expansion of the universe of and by itself will produce particles. Just the expansion of the universe will create particles. This was published in 1939, around the outbreak of the Second World War, when there is no affiliation listed by Schrodinger. He was a stateless refugee. He started this in Belgium. He decided, with war about to break out between France and Germany, I'll move to Belgium. Seems like a good thing to Schrodinger. His political instincts were not very good. He ended up in Ireland during the Second World War, but he was stateless during this period. Now, it was published in 1939, but it was a long time before it received any reference at all, any citation at all, including by Schrodinger. In hindsight, this was a fundamental paper, but Schrodinger never cited it in his lifetime. But it has a strange high citation history, that the citation history of this paper increased sort of exponentially in the last couple of decades. So it's not a usual citation history. I'm waiting for my papers, 40 years or 50 years after being published, suddenly to attract interest. So let me talk a little bit about this paper and what Schrodinger did. The great thing about this paper is it's in English. It was published in Physica. So in sort of the introduction, Schrodinger says, the decomposition of an arbitrary wave function into proper vibrations is rigorous. And by proper vibrations, Schrodinger means that even in an expanding universe, a particle's wave function can be decomposed into proper vibrations, positive and negative frequency modes, even in an expanding universe. He goes on to say that these two proper vibrations cannot be rigorously separated in the expanding universe. That means to say that if in a certain moment only one of them is present, the other can turn up in the course of time. So he's saying if you start with pure incoming or outgoing waves, the expansion of the universe will mix the incoming and outgoing waves. Then he writes, this is a phenomenon, generally speaking, this is a phenomenon of outstanding importance. With particles, it would mean production or annihilation of matter merely by expansion. So he says this is outstanding importance. The expansion of the universe just by itself creates particles. Then he says, alarmed by these prospects, I have investigated the question in more detail. So he's saying, this alarms me, and my editorial comment is, why did it alarm Schrodinger? World War is about to break out. He was a stateless refugee. If the Nazis caught up with him, his life would be at an end. He wasn't alarmed by that. He was alarmed by the creation of particles by the expansion of the universe. So he wrote a paper. All right. And the last part about this paper, he writes, there will thus be a mutual adulteration of positive and negative frequency terms in the course of time, giving rise to what in the introduction I called the alarming phenomenon. Schrodinger's two favorite phrases in this paper were alarming phenomenon and adulteration. So what alarmed Schrodinger in 1939? That there could be the creation of a single particle in the universe per Hubble time, 10 to the 10 years, per Hubble volume of 10 to the 57 kilometers cubed, with a Hubble energy of 10 to the minus 33 electron volts. So imagine somewhere in the universe today, in the next 10 billion years, a particle will appear with an energy of 10 to the minus 33 electron volts. Raise your hand if this scares you. Who is alarmed by this? Schrodinger was. I think in 1939, he imagined that this would be a indication that either quantum mechanics is wrong or the Big Bang is wrong. I don't know what alarmed Schrodinger about this. Okay, so why would the expansion of the universe lead to particle creation? Well, you can think of the expansion of the universe as due to an external field, in this case, an external gravitational field. And the creation of particles from an external gravitational field is a phenomenon that has not been observed, but it's well understood in quantum electrodynamics, and this is known as the Schwinger mechanism. So the idea is that a sufficiently strong electric field in Minkowski space will lead to particle creation. So I'd like to give you just a heuristic idea of how this happens to keep in the back of your mind. So in the vacuum today, we know there are virtual electron-positron pairs in the vacuum. Now, in the presence of an electric field, the electric field will accelerate the electron in one direction, negatively charged electron in one direction, and the positively charged electron in the other direction. And the criterion for particle creation, for ripping the electrons and positrons out of the vacuum, is that you would have particle creation if the energy gained in acceleration from the electric field over a Compton wavelength of the particle exceeds the particle's rest mass. Okay? So if you could, over a Compton wavelength of an electron, accelerate the electron to relativistic velocities, then you can tear the particles out of the vacuum. So you can estimate, just on dimensional grounds, what the critical electric field necessary for this is. The only dimensionful parameter in the problem is the electron mass. So the critical electric field would be me squared c cubed over E, the charge, divided by h bar. And putting in the numbers, this is 10 to the 16 volt per centimeter. So you can't go in a laboratory in a physics department downstairs in the basement and produce electric fields of 10 to the 16 volt per centimeter. So this is a phenomenon that was first discussed by Sauter in 1931, Heisenberg and his student Euler in 1935, Victor Weisskopf in 1936, and the final QED calculation of this was done by Schwinger in 1951. So to have something named after you, it's best to be the last person to do the calculation. Sometimes the first people, but it's usually best to be the last person. This has not been observed, although it's well understood, but it's possible that it will be observed in the near future. So it will not be observed by creating electric fields in the laboratory, but by using the electric fields produced by high-intensity lasers. There was an article written in Nature about using extreme light, and it says physicists are planning lasers powerful enough to rip apart the fabric of space and time. Sounds very violent, doesn't it? To rip apart the fabric of space and time and produce particles. And Gerard Mourou, who won the Nobel Prize shared the Nobel Prize for high-intensity lasers, saying we're going to change the index of refraction of the vacuum and produce new particles. And, the usual bold predictions, talking decades in the future. This is from Mourou's Nobel Prize lecture. This is the intensity necessary of a laser. It's 10 to the 30 watt-centimeters squared. And this is a graph of the laser intensity as a function of time, how it grows. And following the curve, you would have what he describes as light materialization, the making of material particles, electron-positron pairs, from the vacuum due to the high-intensity laser sometime in 2030, which is also the year that supersymmetry will be discovered at the LHC. Isn't that amazing? What an amazing coincidence. So, you know, people are not patient enough to wait so long, but, you know, in astrophysics and cosmology, often you can find in the universe the conditions that you cannot produce in the laboratory. And you can find very large magnetic fields, larger than the critical value of the magnetic field, in astronomical objects such as magnetars. And there was some article that talked about magnetars could has large enough magnetic fields to rip the iron out of your blood from 1,000 miles away. Again, so violent, ripping apart space and time, ripping iron out of your blood. I don't know why violence is so important. Well, the Crab pulsar is pretty sure has a magnetic field of 3 × 10⁻13 Gauss, and magnetars are believed to have magnetic fields at least as large or larger than this critical values. Strong magnetic fields imply the existence of strong electric fields, and there are many strange, not understood phenomena associated with pulsars, magnetars, etc. And perhaps the Schwinger effect is present in the universe today. So this is a way, the Schwinger effect is the production of particles from the vacuum by an external field. And we can also think in rough terms of Hawking radiation as being due to particle creation in an external field. In this case, it's a tidal gravitational field can lead to particle creation. And again, particle creation, if energy gained and acceleration from gravity over a Compton wavelength exceeds the particle's rest mass. So V is equal to C at the black hole horizon. And this is a way to explain Hawking radiation. I don't know whether Hawking or Bekenstein would have liked this explanation, but it's a way you can talk about it to 5th graders. Okay, so what about disturbing the quantum vacuum by the expansion of the universe? Again, we have electron-particle, antiparticle pairs in the vacuum, and you can, again, have particle creation if the energy gained and acceleration from expansion over a Compton wavelength exceeds the particle's rest mass. So you have a particle and an antiparticle in virtual particles in the vacuum. They can get caught in the expansion of space. They're minding their own business. They're just sitting there, but the expansion of space is operating on them. And if the space is expanding rapidly enough, you can create the particles. And the dimensionful analysis would say that the critical expansion rate h would be the mass of the particle. And this essentially is Schrodinger's alarming phenomenon. Now, Schrodinger wrote his paper in 1939. Quantum field theory really wasn't understood and appreciated until maybe 1949. Schrodinger's paper is about quantum mechanics, and now we understand it on the basis of quantum field theory. So Schrodinger's alarming phenomenon, in 1939, he said, generally speaking, this is a phenomenon of outstanding importance. With particles, it would mean the production or annihilation of matter merely by the expansion. He doesn't say why that would be of outstanding importance. This paper was forgotten in the 40s, 50s, and 60s, also by Schrodinger, and it wasn't picked up again until the second half of the 1960s. And the person who really picked it up again was Lenny Parker, who was a student of Sidney Coleman at Harvard. And he picked this up again and did the first quantum field theory calculations of particle creation. He did it for his thesis in 1966, and in a 1968 paper, he wrote, for the early stages of a Friedmann expansion, particle creation, may well be of great cosmological significance, especially since it seems inescapable if one accepts quantum field theory and general relativity. I will accept quantum field theory and general relativity. So Parker says it's of great cosmological significance, but he never says what would be the great cosmological significance. The first attempt to really elucidate a great cosmological significance was made by Yakov Zeldovich in the 1970s, who proposed an application for this. And his idea was the creation of particles through Schrodinger's alarming phenomenon would explain why the universe today is homogeneous and isotropic. So his idea, if you start with an inhomogeneous, anisotropic universe, you would create particles and that would smooth out the inhomogeneities and the anisotropies. This was a brilliant but ultimately failed attempt. Now we understand why the universe is homogeneous and isotropic. Our understanding of it is due to inflation. So this sort of historically, in the 1970s, it was mostly regarded as a curiosity. And in the US, Lenny Parker and his students and colleagues and other people like Bob Wald worked on this, mostly as a curiosity. And in the Soviet Union, there was studies of cosmological gravitational particle production, that should be a P, in the CCCP, Zeldovich, Starobinsky, et cetera, and their colleagues. And in the UK, Bunch, Davies, Burrell, Hawking, et cetera, worked on gravitational particle production, but this was considered sort of a curiosity. It's an exercise of doing quantum field theory in curved space-time. Well, the great cosmological significance was in the context of inflation in the 1980s, and Sasaki, Kodama, Mukhanov, et cetera, all these people realized that gravitational particle production is the origin of the cosmic microwave background anisotropies and the origin of structure and gravitational waves. So finally, in the 1980s, long after Schrodinger's original paper, a great cosmological significance of particle creation was discovered. Well, why stop here? Could there be more? Gravitational particle production is universal. There's a little asterisk here. It says they have bioconformal symmetry violated. I'll go into the detail. Gravitational particle production is not a large effect. The curvature perturbations produced in inflation are 10 to the minus 5. What else could be observable? Well, possibly dark matter, CMB isocurvature perturbations, and CMB non-Gaussianities. So I will finish this introduction by giving you the broad picture of how to understand cosmological gravitational particle production. Now, many of you, probably most, perhaps all of you, have studied quantum field theory in Minkowski space. And how do you classify a particle? You classify a particle by its irreducible representation of the orthogonal Poincare algebra, right? But an expanding universe is not Poincare invariant. There is a time evolution in the expansion of the universe. So defining a particle in a non-Minkowski space where things are changing in time or in space is in some sense, approximate. And this was understood by Schrodinger, Parker, all these people. And the idea is that the cosmological expansion leads to a time-dependent Hamiltonian. The Hamiltonian is not constant in time. And this leads to the mixing of positive and negative frequency modes, and this leads to particle production. So this is the big picture to have in the back of your mind as I go through all of the details. And again, just think of the reason behind this is that the expansion of the universe is converting the virtual particles that get caught in the expansion of the universe into real particles. So let me stop here for a moment and see if there are any questions before I go on to a little bit of technical detail. So far this is sort of a colloquium level presentation, so you can get an idea, basic idea of what's happening. So I can stop here and ask for any questions. And if you have questions during the lecture, please raise your hand and wave it around so I will see you. I don't mind being interrupted. Yes?
On the Jarovic's interpretation of the Berkeley particles, it says they try to understand.
I'm sorry, that's...
Okay, on the Jarovic's interpretation of the particle production, he tried to understand the isotropicity and the homogeneity of the universe from this one. But you mentioned the inflation already solved the problem. So does it mean that even without inflation, it does solve the isotropy and homogeneity?
No, it didn't quite work. Zeldovich could not quite get it to work. And I have this feeling that if Zeldovich failed on a problem, I'm not going to start it. So it's not, I think, a good mechanism to account for the homogeneity and isotropy of the universe. However, what I'm going to do is to use a homogeneous isotropic expanding universe as an external gravitational field to study particle creation. Thank you. Yes, there's a question up here.
Regarding the Mixilla, you pointed out 10 to the 11 or 10 to the 13 GeV. Why those scales are important? Can there be other scales?
Yes. So if you want to produce dark matter just by gravitational interactions, I will talk about mechanisms to do it where the mass is either a micro electron volt or 10 to the 16 GeV. So somewhere in that narrow range between a micro electron volt and 10 to the 16 GeV, you can have dark matter produced only by gravity. Now, most of the ways to do it push it toward the higher end, toward an energy scale associated with inflation. We don't know the energy scale of inflation, but most models have it as 10 to the 12, 10 to the 13, 10 to the 14 GeV. Now, it's our experience in physics that once we find one particle with a particular energy scale, there are many. You know, we usually don't see an energy scale of represented by only one particle. Usually there's a richer structure in physics. So the idea is that the inflaton, the field that's driving inflation, might have a mass of 10 to the 15 GeV. And this is a new energy scale, and there'll be other particles with mass of approximately this. All of these other particles would be produced by gravitational interactions. And if one of them is stable, it could be the dark matter. Okay, let me see what I do here. Blank that. Put this up, and now I'm going to use chalk. So far, this discussion has been using words. What we describe in Chicago is word calculus, only hand waving in words. Now I'm going to write some real equations, and nobody's afraid of equations in this group, right? I find this approach to be fulfilling to me because it involves two things that I really like: general relativity and quantum field theory. And it combines them, and you can't have this without the combination of both of them. So I'm going to give a little bit of background in general relativity and not so much of a background in quantum field theory, just standard graduate school or maybe advanced undergraduate quantum field theory is all that I will require. But general relativity is something perhaps that many of you may not be as familiar with as quantum field theory. So what I'm going to do in these lectures, I'll talk about my conventions, is to use the Landau Lifshitz time-like convention. And you can look at the introductory material in Misnathon and Wheeler to be able to convert these conventions to other conventions. And also there's an appendix in the draft of the review paper you've been given that talks about how to convert different conventions. In particular, I will use for what I consider, this is the West Coast metric signature, also used by, well, I don't know. There's no right convention to use here, but this is the convention I'll use. This is a smart convention. So the metric is real valued and symmetric. And the line element, the proper time, if you will, is G mu nu dx mu dx mu. And there's an inverse metric, and G will be the determinant of the metric. And in order to study GR, you would construct a Christoffel symbol. And gamma mu alpha beta is, there's a bunch of terms, I won't write them all out. G mu nu times D beta, G alpha beta. And there's another term, and then another term still. This is given in the appendix of the paper. And also, there are different signatures for this, different conventions. From the Christoffel symbol, you can construct the Riemann tensor. And this involves derivatives of the Christoffel symbols, et cetera, and there's a bunch of terms. I won't put the indices there because I would screw it up. Then from the Riemann tensor, one can construct a Ricci tensor. and a Ricci scalar. And an Einstein tensor. That's it. That's all of general relativity, almost all you need to know for these lectures.
Assuming the Poisson-free condition.
Yes. I do not have contortion in my in what I would describe. Now we're going to be interested in the interaction between gravity and matter, and we'll take an action approach. And the Einstein-Hilbert action that describes general relativity. This is the invariant volume element, and R is the Ricci scalar. And this will couple to the matter action. With some matter Lagrangian. And the Einstein field equations are recovered from or developed by the variation of the action with respect to G mu nu, that this has to be static, has to be stationary. And this leads to the Einstein field equations. So G mu nu is the Einstein tensor, Newton's constant, and the stress energy tensor for any magnetic fields, any fields you have in the theory. Now I will define a Planck mass and this is sometimes called the reduced Planck mass because it has the value of 8 pi in it. And in particle physics units, the Planck mass is 2.43 times 10 to the 18 GeV. So if you're a particle physicist, that's the Planck mass. If you're a relativist, the Planck mass is 1. And for shorthand, 8 pi Gn, I will call kappa. Now let me say a word about the stress energy tensor. And in calculating the stress energy tensor, in some cases, there is a departure from what you learned in Minkowski quantum field theory. So the stress energy tensor, sort of in this formalism, and this is known as the Hilbert action. Oh, the Hilbert stress energy tensor. And we will often have occasion to find the trace of the stress energy tensor. This will enter a lot in our considerations. Now, other stress energy tensors are defined and used in certain cases. And so this I'll call this the Hilbert stress energy tensor. There is also something that's sometimes called a canonical stress energy tensor. Or near the stress energy tensor. Lost the microphone? Ah. Now I've lost the chalk. That means it's almost time to end the first lecture, but let me finish this a little bit. And, you know, there's different fields. This needn't necessarily be a scalar field. So this is the stress energy tensor that's often encountered in quantum field theory texts. But this will not generally be, is not a general application to curved space-time, because this need not be symmetric in mu and nu. And we know that the stress energy tensor must be symmetric in mu and nu because the Einstein tensor is symmetric in mu and nu. So that's one potential problem. And this stress energy tensor does not properly account for the intrinsic energy momentum say intrinsic angular momentum carried by fields. So the usual canonical stress energy tensor cannot always be used. Sometimes it can for scalar fields, it's fine, but generally it cannot, it's not general. And this canonical stress energy tensor can be modified by the Belinfante-Rosenfeld prescription. And how this is modified is well described in the first volume of Weinberg's quantum field theory book. And the Belinfanti-Rosenfeld stress energy tensor, the modification of that is equivalent to the Hilbert stress energy tensor. So this is one departure of general relativity from what you might, in curved space-time, calculating the stress energy tensor, from what you might have studied in quantum field theory. Okay, so I'm over time for about 2 minutes, so I'll break here for a break, is that right? And when I get back, I will talk about the matter Lagrangians in curved space-time, promoting the familiar Minkowski Lagrangians to Lagrangians in curved space-time. And in most cases, the promotion is straightforward, but in some cases, it requires the use of tetrads, Vierbeins, frame fields, which may not be familiar to everyone, so I'll cover that. So let's take a break. All right, so we're going to involve a lot of starting with familiar quantum field theory in Minkowski space and then promote it to curved space. So now I want to talk about promoting Minkowski to curved space. And this is something that's familiar to basic general relativity. And the steps to do this for scalars, vectors, and tensors, it just sort of involves 2 steps. One, I'll call it A. The Minkowski metric goes to the curved space metric, so A to mu nu goes to G mu nu. And starting with the Minkowski metric, regular derivatives, d mu, go to covariant derivatives, which I will denote by whatever you call this symbol. Now, for scalars, the covariant derivative is just a normal derivative, but for vectors, so if we have a vector, let's say it is a covariant vector v nu, then space-time is going to enter, this is going to be the normal derivative, and it's going to bring in gravity by the Christoffel symbol. And the covariant derivative of a contravariant vector okay, this is something that is probably familiar to most of you. But this prescription does not work for non-integer spin. So for non-integer spin, we're going to use another formalism to promote a Minkowski Lagrangian to a curved space Lagrangian. And so for fermions, we'll use something that's either known as moving frames and this was the description that Cartan, who invented the formalism, used. It's also known as Vierbeins. And this is how it's usually referred to in the German literature, or sometimes tetrads. And this is you often see this in the English literature, but what I will do is to refer to them as frame fields. And perhaps this is not as familiar to those who have studied Minkowski quantum field theory or just basic introductory general relativity. All right, so let me give a 5-minute explanation of frame fields. So at every space-time point, we are going to, let's say, every space-time point x, erect a set of local inertial coordinates. And we will describe these local inertial coordinates by y. So at every space-time point x, we're going to erect a local inertial coordinate system. So it's local, it only applies at an individual space-time point, and it's inertial. Now, in the local coordinate system, in the inertial coordinate system, what is the metric in an inertial coordinate system? It's eta mu nu. This is a Minkowski metric. In a I broke it. In a non-inertial system, in a non-inertial coordinate system, we know how what the metric would be because it's a tensor. So G mu nu of x times eta mu nu. So we erected at every space-time point a local inertial coordinate system. And in this local inertial coordinate system, the metric tensor is the Minkowski metric. And then we can go to some general non-inertial system just by transforming the metric tensor the way tensors transform under general coordinate transformation. So I will define this as E alpha mu of x times E beta nu of x times eta mu nu sorry? Do I need what? Yes, eta mu nu, eta alpha beta. I usually try not to write indices because I usually get them wrong. That's the way you're always right, is not go into too many details. Thank you. So A alpha mu is known as a frame field. A frame field or a moving frame or a Vierbein or a tetrad. The Vierbein means 4 legs in German because there's 4 of them. Tetrad is sort of Greek for set of 4, but these in general I will refer to as frame fields. So in general, when I write the frame field, the early alphabet indices will refer to local Lorentz indices. And the mid-alphabet, so this is alpha, beta, et cetera, and the mid-alphabet, mu and nu, these will be coordinate indices. Now, the decomposition of the metric G mu nu in terms of the frame fields is not unique because we can always have a Lorentz transformation operating on the Lorentz indices, the frame indices, and we can have diffeomorphisms, coordinate transformations, operating on the coordinate indices. So the frame fields are not unique. Then there's an inverse of the frame fields. E alpha mu, such that E alpha mu, E alpha nu, E alpha E alpha mu, E alpha, what am I doing? E alpha nu is delta mu nu. And also Now, vectors and tensors in terms of the frame fields. Oh, let me say that the frame fields, even though it carries two indices and looks like it might be a tensor, it's not a tensor. It does not transform as a tensor. Rather, it's a set of four covariant vectors. So we can carry the space-time indices of, say, a vector field in terms of the Vierbein. So this would be a flat space, and the coordinates indices are carried by the Vierbein. So for an example of this, well, I could also write d mu for the covariant vector. And the way to describe a covariant derivative, shoot. Thank you. Can I blame it on jet lag? I don't know what time it is in Chicago, but it's not 11 a.m. So a covariant derivative in the frame field formalism is the usual derivative plus a spin connection, the moral equivalent to the Christoffel symbol. And the spin connection is related to the affine connection in the frame fields. In the appendix of the review you've been given, we go into a little bit of detail of that. Now, the frame field formalism is a beautiful formalism for general relativity, and it's general. It always works, as opposed to the standard textbook formalism of GR over there, which is not applicable, or it always works, but the frame field formalism always works, but the usual formalism, the standard formalism, does not work for spinors. In particular, consider the Dirac matrices gamma alpha. If we want to use spin 1/2, the Dirac equation, we would convert this to the general curved space-time Dirac equations by something like this. And this then would have the usual Clifford algebra satisfied by the gamma matrices. And I'll just say one more word about this, and we will return to the frame field formalism when I discuss gravitational production of half-integer spin particles. But just let me say that the stress energy tensor, this is a tensor, it can have the frame indices carry things, is 1 over the determinant of the frame field so you would express the action in terms of the frame fields, and then you can calculate the stress energy tensor. And T mu nu, stress energy tensor in curved space, is minus eta alpha beta E alpha mu T beta nu. And here E is the determinant of E. Determinant, which something I'll call the square root of minus G. So in some sense, the frame field is the square root of the metric tensor. So keep this in the back of your mind, and we'll pick it up when we promote, say, the Dirac equation to curved space. So we just can't take the Dirac equation and use the standard formalism to promote it to curved space. Now, in terms of the development of the formalism, the last thing I will do is to talk a little bit about conformal symmetry. And this will be classical conformal symmetry, so I'm not considering the quantum effects. So let's imagine we have a transformation of the metric tensor and it's this is equal to e to the 2 omega of x times g mu nu of x. And omega here is real. Finite function of x. So it's a function of the space-time point. So this is described in various ways. Sometimes it's called a conformal transformation. Sometimes it's called a Weyl transformation. And sometimes it's called a scale transformation. And it's used sometimes in different ways, but this is just, if I define it mathematically, it's clear what I mean. The Weyl transformation, the conformal transformation is not, it's not a coordinate transformation. A coordinate transformation just relabels the coordinates, leaving the metric invariant. Okay, it's just a diffeomorphism, it's a coordinate, it's relabeling the coordinates. It's a coordinate transformation. A Weyl transformation stretches or distorts the metric at every space-time point, squeezes it, makes it grow. It distorts the, it does not leave the geometry unaffected. It changes the geometry. A coordinate transformation does not change the geometry. It's just relabeling the coordinates. So let's take a look. So delta G mu nu is 2 omega of x times G mu nu. So if we imagine infinitesimal Weil transformations, that's how the metric changes. So recall that the matter action is related to that. So the change in the matter action with respect to G mu nu and the stress energy tensor So we know what delta G mu nu is. Go over here. So the trace, this is G mu nu times T mu nu is going to give you the trace of T. And this will be the matter stress tensor. So under a conformal transformation, the matter stress energy tensor, change in the matter stress energy tensor is proportional to the trace of the stress energy tensor. So if the trace of the stress energy tensor vanishes, then the matter Lagrangian is invariant under conformal transformation. So if you have a coordinate transformation, it does not change the matter Lagrangian if the matter Lagrangian is traceless, if the stress energy tensor of the matter Lagrangian is traceless. Now, looking ahead, we will consider the evolution of fields in FRW. And in FRW, the metric tensor in conformal time, A is the scale factor, eta is conformal time. So what does the expansion of the universe do? If you express the metric in conformal time, it is a conformal transformation. It stretches space-time at every point. It's not a coordinate transformation. It stretches space-time at every point. So this is a conformal transformation. As the universe expands, it's a conformal transformation. If the trace of the stress tensor vanishes, then the matter Lagrangian, the action will not feel the expansion of space. If it doesn't feel the expansion of space, there's not going to be particle creation. So the quantum field theory will always behave as if it is in Minkowski space. So cosmological, so a theorem, if you want to call it that, cosmological gravitational particle production requires of some particle requires that the matter action violate conformal symmetry. Furthermore, we will see that the amount of gravitational particle creation will depend upon the amount of conformal symmetry breaking. In some theories, the conformal symmetry breaking, as in for spin 1/2 fermions, conformal symmetry breaking is proportional to the mass of the field. Only by adding the mass to a fermion field is conformal symmetry broken, so gravitational particle production will depend upon the mass of a field. Okay, now I'm going to, again in preparation, talk about the FRW model. FLRW, sometimes I'll just call it FRW, is the Friedmann-Lemaitre-Robertson-Walker model. It's a cosmological universe where space, not space-time, but space, is homogeneous and isotropic. And furthermore, in the early universe, we can assume that the space has no curvature, and we can write the metric And the only parameter that will enter, the only dynamical variable will be the scale factor A. So in general, T mu nu would have 10, G mu nu would have 10 degrees of freedom in the metric. But if it's homogeneous, then you can remove 4 of them by coordinate transformations. So it's 6 degrees of freedom in general. But if you assume it's homogeneous and isotropic in space, then there's only 1 dynamical degree of freedom, the scale factor. So henceforth, we will assume FLRW, the universe is homogeneous and isotropic, and furthermore, that it is spatially flat. Nope. So that's the metric tensor, the inverse metric tensor. Let's write it as a to the minus 2. And the square root of minus g is a cubed. Now, this is the way one usually encounters the FLRW model. But for the purpose of gravitational particle production, we will see that it's most naturally done in terms of conformal time. And I've already introduced conformal time there. Now, if you want to become a cosmologist, you should get an application for your iPhone and your watch that tells conformal time rather than normal time. I live in conformal time. I'm a conformal time person. Not GMT, but CT, conformal time. And in terms of conformal time, we can write the metric as conformally related to Minkowski space. The conformal factor times and we'll see why when we do gravitational particle production, which probably will wait till tomorrow, we'll see why we work in conformal time. Sorry? Conformal, I didn't hear you, sorry. Okay. And in conformal time, the square root of minus g is a to the 4th of eta. All right, so sometimes I will talk about normal coordinate time t, other times I will talk about conformal time eta. And my notation will be a dot will be d by dt, and a prime will be d by d eta. And the usual Hubble parameter describing the expansion of the universe is A dot over A. And this is equal to A prime over A squared. Relating dt, how is it related to A d eta? And of course, today, H is equal to the famous Hubble constant H naught. Now, there's arguments now about the exact value of H naught, and people are arguing about changes of a few percent. H naught is often expressed as 100 H kilometers per second per megaparsec. And people argue about whether H is 67 plus or minus some small number, or H is equal to 72 plus or minus some small 0.72 or 0.67. I can derive on the basis of string theory, H squared is 1/2. Actually, you can derive anything on the basis of string theory. That's one of the theorems of string theory. And I can't really do that, but it's good enough for what I will do today. I can calculate the Ricci tensor and Ricci scalars in the FRW model. Is -3 A double dot over A. And this is in terms of coordinate time or in terms of conformal time. And the spatial components dots. And finally, the Ricci scalar. I write it first in terms of coordinate time because that's probably more familiar to people than conformal time. Okay, so I have the Ricci tensor, the Ricci scalar. I can plug in the Einstein equations. And I would get two equations, one for the 0, 0 component, one for the spatial components. So for the 0, 0 component, is minus kappa over 6 times rho plus 3p. And this is the acceleration equation. Related to A double prime over A. I can use this equation in the spatial components. And this is the Friedman, this is rho, the energy density, T0, 0, and this is the Friedman equation. And another way of writing this is 3h squared, 3h squared is equal to kappa rho, and h is a dot squared over a squared, or a prime squared over a to the 4th. Now, I think the final thing I need to complete this introduction of everything we will use in the standard cosmological model in FLRW is an equation of state for the fluid. So I can write T mu nu as rho plus P here mu nu is the velocity, velocity in the fluid rest frame, so it's 1, 0, 0, 0. So T0, 0 is going to be the energy density, and TII is minus P times GII. And the final thing I need is the evolution of the energy density in terms of the scale factor A. And to do this, one must make an assumption for the equation of state, the relationship between the energy density and the pressure. So if I look at the covariant derivative of the stress energy tensor, bringing in the Christoffel symbols and things like that, the nu equal to 0 component of this involves rho dot plus 3 a dot over a times rho plus p. Now I'm going to assume an equation of state that the pressure is some constant parameter W times the energy density rho. So rho dot is 3 a dot over a times 1 plus W times rho. Well, there's a simple solution to this equation, and that's rho is equal to rho 1, the energy density at some scale factor 1, times A over A1 to the minus 3 times 1 plus W. And H from this equation is the value at this canonical scale factor 1 So we will encounter 4 equations of state. Matter, sometimes called dust, and that's W equal to 0. So if W is equal to 0, rho scales as a to the minus 3. And H scales as a to the minus 3 halves. A radiation equation of state is W is equal to 1/3. So rho is proportional to a to the minus 4. If W is equal to 1/3, rho is proportional to a to the minus 4. And H is proportional to a to the minus 2. An equation of state for lambda. Lambda will describe something that has W equal to 0. I'm sorry, W is equal to minus 1. If W is equal to minus 1, the energy density does not change in expansion, and neither does H. Well, what else could be interesting other than W equal to 0, W is equal to 1/3, or W is equal to minus 1? Let's pick W equal to 1. This is known as kination. It's when the equation of when the energy density is dominated by the kinetic energy. If W is equal to +1, rho is proportional to a to the minus 6. And H is proportional to a to the minus 3. And we will encounter these equations of state in gravitational particle production. Now, take another 2 minutes to close off this introduction. By solving for these simple models, well, let me pick this up tomorrow because it will take longer than 2 minutes. I'm almost finished, then I'm going to talk about inflation, the inflaton field, how to convert a quasi-de Sitter space into a matter-dominated expansion, and finally into a radiation-dominated expansion that will complete the description of the background space-time. So we're going to take this as a semi-classical approach. We're going to assume that the gravitational field is classical, and we're going to impose a quantum field, a spectator field, evolving in the classical evolving gravitational background.